In this video, I want to look at energy diagrams. And I'm sure you've probably seen these before. So this is where we have energy increasing on our y-axis. So if I draw something higher up, it's higher in energy, lower down is lower in energy. And then on this axis, our reaction is progressing. So as I go from left to right, I'm going from reactants to products. And then generally, we're going up in energy, and then we come back down to some point. This reaction, the way that I drew it, it only actually has one step. We'll draw some that have a couple steps, but just to label our parts, I have my reactant. Over here, I have my product. This part up here is my transition state. Remember, my transition state, I said, was the highest state during my reaction. That's where we have our partially broken and partially formed bonds. So R is my reactants. TS is my transition state. And then P are my products. And then my energy difference between my reactants and my transition state, do you guys remember what that was called? Right, it's the energy that I have to put into it. Sometimes it's called the barrier to our reaction, right? To get from reactants to products, this is the energy that has to go into it. Yeah, if you guys said activation energy, you're right. So often abbreviated capital E with a subscript capital A. So EA here is my activation energy. And it's the energy that you need to put into our reaction. So to get from reactants to transition state. So the energy that must be supplied for the reaction to occur. Now notice I do have my products lower in energy than my reactants. So overall, we're actually losing energy, but I do have to put energy into it. So I'm gaining less energy than I'm getting out of it, but I do have to put energy into it. That doesn't mean that all reactions have a net energy gain, right? This one actually has a net energy loss because I'm drawing those products lower than I am reactants. What is that energy difference then between reactants and products called? Yeah, our book is actually using delta H. Delta H, remember, is our enthalpy change. It could be called delta G, right? My Gibbs free energy change. Not all reactions only have changes in heat, right? If we had changes in entropy also, then we would talk about our Gibbs free energy change. I like to use delta G versus delta H. It's just more accurate, but our book does use delta H, so honestly I would take either one of them. But remember, delta H is my enthalpy change. Remember, enthalpy was the heat of my reaction. Is it gaining heat energy or is it losing heat energy? Right, if we had a negative value for delta H, right, that means that my final enthalpy is less than my initial, right? Remember, every time we see that delta, it's always going to be final minus initial. So if it comes out to be negative, that means that I have less, right, when I'm done, because I'm subtracting a bigger number from a smaller number for it to come out negative. So if I have a negative enthalpy change, it means that I'm losing heat energy. And in the reaction and the energy diagram that I drew, it would have a negative value, right? My products are lower in energy than my reactants are, right? H final is less than H initial, if I'm saying that change is due only to enthalpy. So heat energy is lost. And then we had a special name for that type of reaction. These were exothermic. So according to the diagram that I drew, it would be an exothermic reaction. a positive enthalpy change, if I did that, I would draw my products higher than my reactants on that diagram because we gained heat energy, right? My final enthalpy is greater than my initial enthalpy. So heat energy is gained. And we would say it's endothermic. So looking back up here, I did write delta G as an option for our energy change between reactants and products. That is the way that I had learned it, and I actually prefer it because it's usually not just a heat change, right? We also do generally have a change in entropy. So if we're going to look at it in terms of delta G, right, my Gibbs free energy change, remember that if I have a negative value for delta G, what does that mean for my reaction? Do you guys remember for 152? Yeah, hopefully you're remembering a little bit about this. It means that it's a spontaneous reaction. Remember, a spontaneous reaction is always taking us towards equilibrium. And I can't spell, but we already know that. Spontaneous reaction. If I have a positive value, that is non-spontaneous. Remember, a spontaneous reaction is one that occurs on its own, right, without an external influence. It doesn't mean it's fast, right? Don't get spontaneous and instantaneous mixed up. It could take a million years and still be spontaneous. It only means that if I leave it alone, it's going to happen, right? It's going to occur on its own without an external influence. Things want to be more stable, so because my products are lower in energy than my reactants, I will spontaneously go in that direction. So just kind of our little reminder, spontaneous reactions, these occur on their own. Without an external influence, which is kind of redundant. I do have some names if my free energy change is negative or positive. If it's negative, it's called an exergonic reaction. And I don't use these very often, but exergonic. And then endergonic if it's non-spontaneous. I tend to just say spontaneous versus non-spontaneous, but those two words would apply. So instead of endo and exothermic, I have endergonic and exergonic as those terms. So going back up, I could say this is a spontaneous reaction if that overall energy change is delta G. It would be an exothermic reaction, right? I'm losing heat energy if that overall energy change is delta H. I do want to review entropy real quick since we've mentioned it. Remember entropy, that's going to be S. So I'm going to look at my entropy change, delta S. And we said that this was a measure of molecular disorder, or entropy is a measure of molecular disorder, or randomness. So if I have a positive entropy change, that means that entropy is increasing, right? S final is greater than S initial, so it's becoming more random, more disordered. And kind of the easiest example is if I was to go from a liquid to a gas. Remember, in a liquid, I have lots of connections between particles, right? Lots of intermolecular forces. When I go to a gas, I've broken those. When I'm a liquid, I have a definite volume because I do have some connections between those. In a gas, I don't, because one of those molecules can go off in one direction Another can go off in a different direction, and they can expand to fill up whatever space we have. So I'm going from something that has connections between them and is somewhat orderly to something that has no connections and is very disordered. If I run from a solid to a liquid, I'm also increasing entropy. In solid, it's very ordered, right? Lots of connections. It has a very distinct pattern if it's a crystalline solid. And I break some of those connections when I go to a liquid. It no longer has a definite shape, so it's more random. So when I go from a solid to a liquid to a gas, I'm increasing in disorder. I'm increasing in entropy. The other direction, I have less randomness than I started out with, so it's becoming less disordered. Or more ordered, however you want to think about it. I like to think about it this way because disorder is what I'm measuring when I measure entropy. So I'm becoming less disordered. So if I went from a gas to a solid, I'm tightening it up, right? I'm forming connections. And then if I go from from a gas to a liquid, I'm making those connections. And then a liquid to a solid, I'm making more connections. If I was to reverse those arrows, they would have negative entropy changes. So both of those things tend to contribute to the spontaneity of a reaction. So if I had, let's say, an ice cube, and I just, at room temperature, I set it on the table, it's going to melt. It's increasing in energy, right? I have to put heat energy into that ice cube to get it to melt. So it's going to be disfavorable with respect to enthalpy, right? It's gaining energy. We said things want to lose energy, right? If things occur spontaneously, they tend to be losing energy. In this case, though, it's gaining heat energy. It is actually going to lose free energy because it's becoming more disordered. So it's disfavorable, right, to melt that ice cube when I'm only considering heat. But when I consider entropy, it's favorable. So it's increase in entropy is greater than its decrease in enthalpy, that overall is still going to be favorable. Or that it's increase in entropy, sorry, so let's write that down. So if I have water and it's solid and I go to water, liquid, right? We have to add heat energy to it, right? It's not going to melt if it doesn't increase in heat energy. So I have an increase in heat energy, but I also have an increase in entropy. So this is actually unfavorable, right? Things don't want to increase in energy, but we do have a law of thermodynamics that says that total entropy does increase. So because I'm increasing in entropy, this is going to be favorable, right? Entropy tends to increase spontaneously because it's more probable. So overall, it is a spontaneous reaction, right? My Gibbs free energy change is negative. So even though it's gaining heat energy, right? It's gaining heat, overall, my free energy change is negative because the amount of entropy that it's gaining, right, overrides the amount of heat that it's gaining. So I really like to think of it in terms of free energy changes. But again, going back up to my diagram here, the book is using enthalpy changes. So I will take either one. But do know delta G, if I tell you, it's exergonic, or if I tell you it's a spontaneous reaction, know how to draw that. Like I may give you delta G information and ask you to draw it. If I give you one and ask you to label it, then it's up to you which one you want to label it. So I do want to do an example of one where I have two steps. So make it a little bit longer. I still have energy increasing. I still have my reaction progressing. So we'll start somewhere here. I'm going to go up. I'm going to dip down. I'm going to come back up, and we'll make this one spontaneous again. So we're going to come down a little bit further. So this is one where I'm going to see an intermediate. So this is going to be my reactants. This is going to be my product. I actually have two transition states. And then this dip is going to be my intermediate. So I'm just going to put an I there. I is my intermediate. when we were looking at our mechanisms, right, I said an intermediate is still high in energy, but it's not as high in energy as my transition state. So it does dip down a little bit. I actually am going to have 2 activation energies for this one. So activation energy 1. And then between my intermediate and my transition state, my second transition state, I am going to have another activation energy. So activation energy 2. I still have only 1 overall energy change. I said I was making this spontaneous, so I'm going to write it in terms of delta G. If I would have said I'm going to make it exothermic, then I would write it in terms of delta H. So the one mechanism that we looked at a little bit ago, right, I had this alkene, and then I don't remember if I used bromine or chlorine, but it's the same mechanism either way. Oop, I think I used hydrogen. It was HCl. I should have looked. And then we broke that, and I had that carbocation intermediate. I just want to draw it nicer. And then we had chlorine add on to that carbon. Right? So if I was to label all of these, this is A, so that includes both the alkene and the HCl, and then B, and then C. B is that intermediate, so A goes here, right? B, and then C. And then I did draw those 2 transition states. I had said that you didn't need to, but I wanted to just kind of reiterate what they were, right? So we had that transition state where I had a dotted line here because I was breaking a bond, forming a bond. Forgot to write the hydrogen, and then breaking a bond, right? And then between my intermediate and the product, we had another transition state where I was forming the bond between the carbocation and chlorine. So let's, I don't know, call these, my numbers are order, D, A, B, C, D, and E. Then D goes here, right? It's my first transition state. And then E is going to go here. Let's move that B out of the way. I want you to see the I. So I'm starting out with my reactants, right? I'm going through this transition state, and then I'm going down a little bit in energy to this intermediate. I'm adding more energy to it, right? My activation energy. I'm going through this transition state, and then I'm finally coming back down to that product. So we always have transition states, right? If I asked you to draw the mechanism for this, I'm generally not looking for those transition states that I drew in blue because we do have the intermediate, but they do exist, right? If I look at my energy diagram, I'm going up in energy, and then I'm coming down to that intermediate. I'm putting more energy into it, and then I'm coming down to that product. Again, activation energy is the amount of energy that you have to put into getting where you want to be, right? I don't know if you've had me before, you've probably heard this silly analogy, but I always think of these energy diagrams as like going to college, right? Like the reason you want to go to college is because you want to be more stable, right? You want to be more stable, a good job, retirement, whatever it happens to be. And to get there, you have to go to college. So you have to put all of this effort into it, right? You have to put all of this energy into it. You have to get all stressed out and question why you're doing it and make yourself crazy. But the reason you're doing it is you're going to be down here. So I always think of like going to college as like that barrier to your more stable future, right? And you guys are in organic, so you're like, you're up here somewhere. Maybe a little bit more stressed out because you still have 236 to take, but you're almost over that energy hill. This was one, I'm never out of analogies. This is like if you go to like grad school or like pharmacy school or whatever it happens to be, right? You're in organic, right? You finally get over that energy hill. You get a little bit of a break and you're thinking things are pretty good, and then you get into pharmacy school. You add all that energy into it. and then eventually you come back down. So activation energy, right? Sometimes you have to put energy into getting where you want to be. I do want to talk a little bit about the relationship between equilibrium and our free energy change. I did mention earlier that reactions spontaneously go towards equilibrium. There is a link between those two. And essentially, the position of our equilibrium depends on the relative energies of my reactants and products. So before we get into those details, let's just review equilibrium real quick. So if I have A going to B, B can go back to A, right? So we have a reaction that proceeds in both directions. When it's at equilibrium, so EQ for equilibrium, the rate in the forward and reverse directions are equal. So be really careful. Just because I'm drawing arrows going in both directions doesn't mean we're at equilibrium. We don't know that we're at equilibrium unless those rates are equal, right? If I'm forming B with the same rate that B is decomposing back to A, then I'm at equilibrium. And then I guess also be careful. It doesn't mean that the amounts are equal, right? My concentration of A could be a gazillion times more than my concentration of B, as long as it's going from A to B and B to A at the same rate. So my amounts or concentrations do not have to be equal, right? We've had a few questions already, like when we were talking about acids and bases, and I said which direction is favored at equilibrium, right? If my amounts were equal, there wouldn't be a favored direction, right? It would be equal. And the equal part of equilibrium means the rates are equal, not the amounts, right? My rates are equal. Need a bigger highlighter there. So the rate in the forward and reverse direction are equal, right? The concentrations or amounts of A and B do not need to be equal. We have talked kind of real briefly about our equilibrium constant. We had Ka and Kb before. I'm just putting Keq in case it's not an acid or a base, so just a regular reaction that goes back and forth, right? That doesn't involve acids and bases. And we know that's defined as my concentration of products over reactants. And then it's raised to a power equal to their coefficient. So if I went up and put coefficients of, let's say, m and n on them, then I would raise A to the m power and then B to the n power. So if I had 2 moles of A would be raised to the second power. If I had 3 moles of B would be raised to the third power. So however many moles I have, right, the coefficient. So products over reactants raised to a power equal to their coefficient. And I had said at the beginning of this that the position of the equilibrium depends on the relative energies of reactants and products. So the position of the equilibrium depends on the relative energies of my reactants and products. So is my product higher in energy than my reactants or vice versa? And you did have an equation in 152 that related our free energy change to our equilibrium constant. So delta G was equal to a negative R, which was a gas constant, T, which is my temperature in Kelvin, times the natural log of my equilibrium constant. Our book is actually writing it using log base 10, so it uses the 2.303 RT times the log of KEQ instead of natural log. We're not going to do math problems with it. The only part I want you to notice is that my free energy change is equal to the negative of whether it's log base 10 or natural log, it really doesn't matter, of KEQ. So we're not going to plug numbers in, right? Our book is using, again, delta G is equal to negative 2.303 RT log base 10 of KEQ. And again, the part that I want us to focus on is that there's delta G's on one side, there's a negative sign, and then the log of my equilibrium constant. So what this means for us is that if my equilibrium constant is greater than 1, so I'm going to go back up and look at this, right? If my equilibrium constant is greater than 1, that means my concentration of B is greater than my concentration of A, right? Because when I divide them, I'm getting a number that's larger than 1. So my number on top has to be bigger than my number on the bottom. So that means my products are favored, right? Sorry, having to scroll back up. B is my product. So if I have more B than A, products favored at equilibrium. So when I was down here, when I say my equilibrium constant is greater than 1, I'm saying my products are favored. And we are going to relate that to energy in a minute. If I was to do the opposite, right, now my number on the bottom is bigger. So my concentration of A is greater than my concentration of B, and reactants are favored at equilibrium, right? Remember, my amounts don't have to be equal. I can favor reactants or products, but my rate needs to be equal. So back down to this, if my equilibrium constant is greater than 1, then when I take the natural log of that positive number, it's going to come out to be positive. So the natural log of KQ is positive. And then if we look at our formula, I have that negative sign in there. So delta G is going to come out to be negative. And remember, if we have a negative free energy change, it means that my free energy change when I'm done is less than when I started, so I'm releasing energy. Which is favorable, right? We're going to favor the side of the reaction where it's more stable. So if energy is released, it's becoming more stable, so we're going to go in that direction. So forward direction is favored, right? We don't want to increase in energy. We don't want to become more stable, right? We want to become less stable. Kind of using my college analogy, right? You wouldn't put all this work into doing something if you're just going to end up worse off than before you started, right? So we want to favor the more stable side. If my equilibrium constant is less than 1, my natural log, or log base 10, is actually going to be a negative value. So the log of something less than 1 comes out to be negative mathematically. So again, going back up to my formula, because I have this negative sign here, a negative times a negative is going to give me a positive. And I know that energy is absorbed, and we don't want to do that. So the reverse direction is favored, right? So equilibrium favors reactants. The opposite of a spontaneous reaction, which is what my first example is, right? If my free energy change is negative, this is spontaneous, is non-spontaneous, meaning the opposite direction of a non-spontaneous, which is what this is in the forward direction, right? If it's non-spontaneous in the forward direction, then it's going to be spontaneous in the reverse direction. They're always going to be opposite. So if A going to B is spontaneous, B going to A is non-spontaneous. If A going to B is non-spontaneous, then B going back to A is spontaneous. So if delta G is positive in the forward direction, it's going to be negative in the reverse. We're going to favor reactants. So I just do want to do a couple more example energy diagrams. So just kind of asking us some questions about it, and then I am going to add a little bit. So let's do this one. Just kind of looking at the difference between them. So we're going to label reactants, products, transition states, any intermediates if we have them. We're going to label the axes, and then we're going to identify our activation energy and then our Gibbs free energy change and say if our reaction is spontaneous or non-spontaneous. On a test or quiz, I would write all of that down. Here, we'll just do it all together. So axes first, I do have energy increasing on that axis, and then my reaction is proceeding on this axis. So I'm going from reactants to products, which means I'm starting out with reactants, and I'm ending with products. I said we're going to label transition states and any intermediates. This one does not have an intermediate. If we have an intermediate, we'll have a little dip and then another transition state, right? Every time we have an intermediate, we're going to have more than one reaction step, right? Reactants to intermediate, from intermediate to products. So each of those will have a transition state. Here I only have one transition state. I do not have an intermediate. So transition state, no intermediate for this one. My activation energy is going to be that energy difference between my reactants and my transition state. If I had an intermediate, my second activation energy would be the energy difference between the intermediate and its transition state, right? The transition state going to the next step, because the intermediate is the reactant for that reaction step. So activation energy. And then my Gibbs free energy change is always going to be the energy difference between my reactants and my products. And then is this reaction spontaneous or non-spontaneous? This is non-spontaneous, right? The reason we know that is that the energy of my products is greater, right, than the energy of my reactants. So this one would actually be favored in the reverse direction if this one went in both directions. So non-spontaneous, the energy of my products is greater than the energy of my reactants. I have a positive value for delta G. It would be an endergonic reaction if we wanted to use those. I'm going to draw another one here. And we're going to make them both one step again. Those axes should be kind of similar. I'm just going to copy the one just to keep my scale to the same thing. And then I'm going to start here, and I'm going to go up, and I'm going to come down. And then on this one, I'm going to start relatively in the same place. I'm going to go up further, and then I'm going to come down to relatively the same energy. That's kind of a really ugly, I want to try it again. I actually kind of went, instead of having it slope down, it actually kind of went out and then came back in, which doesn't make any sense for my reaction progress. So I'm going to go back up further, and then I'm going to come back down to roughly the same thing. So I want the energy of my reactants and products to be the same on both of these. The only difference between these two should be my activation energy, is how I wanted to draw it. So my free energy change is going to be the same for both of those, is how I wanted to label it or draw it. So my activation energy for this one compared to my activation energy for this one. It's not very straight. So energy is still going up, my reaction is still proceeding. You should always label axes. Okay, so comparing these two, reaction A to reaction B. Right? Reaction A has the larger activation energy. So which one of these reactions is going to take longer if we want to think in terms of kinetics? Remember, when we talk about kinetics, we're talking about the rates of reactions, right? What is the time that it takes to go from reactants to products, right? How quickly do products appear? How quickly do reactants disappear? Yeah, hopefully you're thinking that A is going to be faster than B, right? If you remember catalysts, right? Catalysts speed up reactions by lowering that activation energy, right? Implying that the bigger the activation energy is, the slower it is. The lower the activation energy, the faster it is. So reaction A is faster than reaction B, right? Reaction A has the smaller activation energy. Essentially, when we're going from reactants to products, what happens is my reactants need to collide with each other. And they need to collide with enough energy to break their bonds. And that's what my activation energy is. And if the amount of energy that you need to do that is smaller, then it increases the odds of those collisions having enough energy, right? Just a sheer on odds thing. If you don't need as much energy, more collisions will have enough energy that's equal to or greater than that activation energy. If that activation energy is large, then you have fewer of those collisions, right, that have the right amount of energy. There's also orientation, right? They have to collide with the right orientation also, not just the correct energy. But here we're just looking at energy. So the faster the reaction, the smaller its activation energy is going to be. We are going to talk more about kinetics in chapter 7. There is some in this chapter, but I'm going to save most of it for chapter 7. So right now, all I want you to be able to do in terms of the speed of our reaction is be able to look at an energy diagram like this and tell me which one's faster. So smaller activation energy is going to be the faster reaction. I could give you one that has multiple steps in it. So let's go to A. Let's go this way. Let's do a little one. So energy, reaction. How many intermediates do I have in this one? Hopefully you guys said 2. I have that intermediate, which actually isn't much higher in energy than my reactants. I have this intermediate, and then I have my product over here. This would be a transition state, and then another transition state. And then I have 3 activation energies. Right? Activation energy 1. So this reaction is taking place in 3 steps. My second activation energy, and then this one is small. My third activation energy. So I could ask you which step is the fastest, right? My last step, right, is going to be my fastest because it has a smaller activation energy. If I asked you which was the biggest, it's hard to tell, but whichever 1 or 2 has the bigger activation energy, I would make it easier to tell, but those 2 are pretty close. So you could actually say the speed of the first step and the second step are pretty similar. My third step is much quicker. I know I have 3 steps because I have 2 intermediates, right? I'm going from reactants to intermediate 1, we can put a 1 on this, to intermediate 2, we can put a 2 on that, to products. And we know that this is my fastest step. We know that these are pretty similar. Let's actually do one more. I said I would save kinetics, but I do want to do one more kind of kinetics related thing. So energy, reaction. So I'm going to go up, I'm going to dip down, and then I'm going to come down. Was that last one I did, is that spontaneous or non-spontaneous? Good. Hopefully you guys said spontaneous, right? My products are lower in energy than my reactants. My forward direction is going to be favored at equilibrium. This one I also drew spontaneous, right? My products are lower in energy than my reactants. My question to you on this one is, what is the rate determining step? Again, we're going back to your kinetics past from 152. In chapters 7 and 8, we are going to be talking about rate determining steps, and I will review it more then also, but just kind of a little preview chapter. So our first step or our second step, right? Our first step is going from reactants to this intermediate. My second step is going from that intermediate to my products. Again, we always have a transition state between each, right? That's where we have those partially formed and partially broken bonds. So my first activation energy and my second. So who remembers rate determining steps? If you guys are going with the first step, you're correct, right? Our rate determining step is the slowest step, right? Remember, our overall reaction can never proceed faster than our slowest step. So whichever one's slower is going to determine the rate of that reaction. So the slowest step of the, we could say, mechanism is our rate determining step. RDS is our abbreviation for rate determining step. So remember, the bigger the activation energy, the slower, right, that step is. So because my first activation energy is larger than my second, right, my first step is slower than my second, my first step is going to be my rate determining step. So the first one, right, larger activation energy.